Great. So I'm going to talk about some stuff I did the past like 2 months, I think, or something like that. So it's not a lot of time, but I wanted to understand this agentic coding thing that people were talking about, and like how does it work? How do you do it? And so I tried using open code, couldn't get it to work locally, and then I gave up and I started building my own. Because that's how I learn. I can't understand other people's work. So this is me trying just to figure things out, and that's what I'm going to try to share with you. I'll just tell you a little bit about who I am and where I'm from and what we do, and then it's going to be all about like, okay, what am I doing and how am I doing it, and then something for the future to think about, something to consider. Please ask questions. Don't be afraid to interrupt me. This is not going to be a very long presentation, and I think it's important that people, can follow along. If you have a question, somebody else probably has the same question. So I'm John. I've been doing software engineering for like 25 years. I currently work at MSAB, hence the cap and the name tag, and we work in something which is called digital forensics, or sometimes digital forensics incident response, something, I think. And we do break into people's phones on the behalf of government. So it's legal, but it's kind of gray area, really. like we there's black hats and white hats, right? We are neither. Sorry? No hats, no. Because it's like, yeah, it's a good place to be. Like it's filled with a bunch of people who kind of want to make the world a better place and all that, and it's actually quite interesting place to be. And it's a complete Swedish company. We have a brand new office on Sveavägen and all that, which is kind of fun. So that's kind of this. But yeah, so why bother with local AI? Like why? Because like you can just rent stuff in the cloud and just do that instead, and like, so why bother with local AI? But there's a couple of reasons for that. Like maybe you did buy, like I actually did buy a very expensive GPU, but it was for playing games. So I had that, and I'm like, okay, can I use this for something? But and like I'm not really great about this thing with the credit card. Like I don't like subscriptions. It's like it's just I'd rather pay a lot of money up front. I mean, I told you a little bit about what we're doing. And so maybe that's not really appropriate things to be doing on like frontier models in the cloud. Like we do get, like we do experiments, of course, and we get emails telling us to stop. So, and yeah, token spend is a thing now as well. I added this last night. It was, our CTO is kind of running around like, I think this is going to be too expensive. So I mean, I guess I'm cheap. This is what I have. It's an RTX 4070. It's a 3-year-old GPU. It cost 7,000 SEK when I bought it. It's an Ada Lovelace architecture, so it's the last generation. It's not Blackwell, which means I'm using Q.12, not Q.13. Q.13 has a tile-based programming paradigm for Blackwell, which is kind of different. So if you ever wonder which one to pick, like are you doing tile-based programming or are you doing other stuff, this is why. It's like a 200-watt GPU, so it's like nothing crazy in that. And then I have a nice 5950X processor and plenty of system RAM. But this is more than enough to actually do interesting things, as we'll see. So at the time I started experimenting with this stuff, I was trying like all kinds of different models, like whatever I could actually get running on my computer. But sort of at around this time, and I think it was in early April, Google released Gemma 4, and they had these edge models, which are really compact. So it's about 8 gigabytes of data, and it's multimodal, which is kind of cool. So it can do text, image, and audio. Interestingly, the edge models do audio, but the other models, the bigger ones, actually don't do audio. So okay, it's just in the edge model, whatever. At some point, I'm kind of like I'm a bit like dumbfounded by the fact that this is 8 gigabytes of random numbers, and it's capable of doing all these things. Like it has reasoning traces. You can do 128K of context on them. They can do image recognition, OCR. It does support PDFs. There's some built-in support for PDFs, which is great because a lot of documents are in PDF. I haven't actually figured out a way to actually use that feature specifically. I don't even know if the inference engines actually support that, but it's in there. What else? Yeah, They have native function calling, code generation, and the audio stuff we talked about. It's kind of awesome.
Stuff seems to be eating a lot of context, so watch out.
Yeah, right. What was the D?
If you do PDFs, it eats.
Right, yeah. And yeah, it's funny because I looked at how the way Claude does PDF skills, and like it has these strategies, and the last thing it will do is it will actually render the PDF, take screenshots, and then feed them back into the model, and then get the content that way. So that will work for like vector stuff, or if the text is not actually, it's just shapes inside of the PDF, then they do that. It's kind of interesting though. It's kind of like, if you want to figure out what these things do, you can just actually ask them to tell you. They're very friendly. They're like, oh yeah, I'm doing these things and I'm doing all those things. Okay, cool. So I can just do the same thing. So it's kind of a free-for-all. Yeah, but it's kind of cool. It's like I call it the potato model, I guess. But it's kind of handicapped, but it can still do things. So I tried some different inference engines. These are just the ones I tried. I think VLLM seems to have very good support, but it's like 1 billion Python packages. And it doesn't run on Windows. I actually use Windows, so it wasn't a great experience for me. I started out with Ollama, and I think that was a good start. It's really like out of the box experience of Ollama. It's like click, click, click. Okay, we're gone, and we're done. So that's good. But then when you want some control and you want to do different things, like it doesn't really expose all the things, and it's just sitting on top of Llama CPP, which is my preferred choice at the moment. It is just a bunch of binaries, and then you have to pick your runtime, and there's a couple of them. And I think that's nice. So yeah, this is what it looks like. There's a bunch of files you just dump into a folder, then you have this, and that's what you run. And I think this is the right way to package an application, right? You could have less DLLs, I guess, but it's kind of cute because they have special code paths for the different CPU architectures, and there's some cute DLLs somewhere here as well that didn't fit on the screen.
And the NSA DLL.
Yeah, exactly. So this is how I run it. These are the parameters I use on my 12 gigabytes of VRAM that I have. And there are some defaults that you want to tweak for various reasons. For instance, I don't really need parallelism. I'm actually running everything sequentially. So it's kind of slow that way. You could, of course, do parallelism if you had more VRAM. But if you increase the parallelism, you have to duplicate the context window. So you have to pay for the memory requirements for the context windows you do that. So when I tried to fit some other models, I ran into problems, and I realized I could do these things. Same thing with fit target. It's just a way for me to say that normally it will reserve 1 gigabyte of space. It won't actually touch that. And this is just a way for me to say that you can actually reserve more if you want to. You just have to leave this little bit.
Give it 6 months and you will have multiple GPUs. So
yeah. But so this is just, and then I do these. The Llama CPP stuff, they have this GGF format. Like you can get most of this stuff just on Hugging Faces. It's just that they repackage them. So if you click on a model, it might not actually run with Llama CPP. But you can usually find if you look for this GGF stuff, you can find the thing you want. And then there's I just 8-bit quantization for the context. This just makes the context window smaller. And I use the 8-bit quantization of the model as well. It's fine. I've tried lower quantization. I've tried 1-bit stuff, and sometimes that works as well. Like you can just try things. But you quickly run into all kinds of problems. You don't really know if they're caused by quantization or if they're caused by, the model itself. So it's an interesting area. But this will get you going, and it fits nicely in RAM. And if you do, when you're running it, it's actually kind of nice. It just will tell you that, oh yeah, this is how much memory we're going to use, and I will have this much left for room for you. And then it's going to tell you, yeah, so this was the context parameter we did, and it will tell you like, oh yeah, I need this much and this much. And I think this weighs in then at like at slightly above 9 gigabytes for everything, and I had 12. So then I have a little bit extra, which is good because then I can use like an embedding model on top of that, which is just a couple of megs, hundreds of megs on top of that. So there's still some space. And it's kind of cute when everything is up and running like this, because you can see down here then what the CPU versus GPU usage is, and I'm like asking it to do things, and it's like it's using most of my VRAM. It's very little CPU usage and mostly just running on the GPU, and that's what you want to see, right? As soon as the CPU usage goes up, it's because the model is no longer on the GPU and you're moving stuff over the PCI Express bus and it's just not fast enough, and that's when it goes slow. So as you can see, I'm getting 60 tokens per second, which is not slow, but it's not super fast either. But it's very workable. So this is enough that I'm not getting annoyed when I'm trying things, so I can move on from here. And also everything, this is private. And this is just the web interface that they give you. So when you launch Llama CPU, this is what you get. And it looks kind of like what everyone else is providing. So you kind of have something that they can actually use. And
Windows reserve like 2 gigabytes of VRAM anyhow for just the Windows GUI?
That I have actually not had any problems with. Yeah. That could very much be the case that Windows is grabbing something, but I think it gets paged out. It's interesting because if I look into Task Manager and I look at how much my GPU actually has, it has actually allocated a lot more. So it's like the kernel space is mapped onto the GPU as well. So it looks like I have like 47 gigabytes of VRAM, but the dedicated portion is only 12 gig. And I have filled that up without problems. But yeah, you'll just have to try things and see what happens. Okay, and so what happens when you run a small model? Like, what can you expect from it? Like, and yes, it like all of these things happen. Like, it gets worse, it fails more often, and you need redundancies. But if you're trying to figure out what I want to do is I want to build this harness, right? The thing around the model that orchestrates the things I want to be doing. And so it's just that you're just going to run into problems faster. And so you can fix those, like you can build guardrails around those problems. And when you put a more capable model in there, it should behave better, it should be better. And I've done some experiments. Sometimes I plug in Grok or Kimi. I did buy some compute from Evrock. And it works fine. Then it just does things more accurately.
So
more
efficiently. Hyper-intelligent 4-year-old, not hyper-intelligent 12-year-old.
Precisely. But if you just want to play around with things, you can do that. I think I did this wrong. I had this idea, okay, so but I'm not going to give the model free reign over my computer, and I'm not going to allow it to make mess. So I started making I didn't sandbox, I didn't run it in a container or anything like that. I was just running everything on my computer, and I started giving it tools to just do everyone know what a tool is? Does anyone dare to not say yes? But anyway, it's like a tool it's just a way for it to just invoke a function in your code, and it will put some parameters and return a control flow back to your program, your harness. And so it had very limited capabilities, and it's kind of retarded to think you should do it that way, because you're giving it probably arbitrary code execution capabilities anyway in the end, because it is allowed to write code, it is allowed to run that code. So if it wanted to, it could just create a program to do what it can't do with the tools I've given it. So you might as well, just let it have more freedom, I guess. And that's what the Hermes harness is doing. It's a sort of it can introspect itself and rewrite itself and stuff like that, which is kind of cool, really, but also a bit crazy. So I am a control freak, so I went down this route, and it worked. And it's just based on if it can read write files inside of the directory I'm launching it from, and that's about it. This is just a simple demo. I wrote I have a system to create sub-agents, so I wrote a browser thingy. I had to help it a bit along. I played around with various different system prompts and skills and all that to make it do things. The way this works is kind of interesting because it is actually using a WebSocket to connect to Chrome, and then it's using the CDP protocol to just do whatever it wants with Chrome. The only thing I've done here which is a bit special is that I've allowed it to feed screenshots back into itself. It will have to figure out how to navigate the page. that is kind of, that happens very badly most of the time. Like it's often it's doing things like, I don't know if you saw that in the consent screen, but the buttons were like uppercase, but that's a CSS transformation. The text is actually lowercase. So in the prompt to the browser agent, I actually told it, like, don't use case-sensitive comparisons, like use case-insensitive comparison, like silly things like that. And it also has a way to actually complain. That's something I stole from Lovable, but I did the vent thing, so that if it's like, it can get stuck, like failing and like running scripts and they're not working and it get errors. And then it can actually call out a tool. It says like, okay, yeah, I've tried this, I'm giving up, it doesn't work, and then, yeah. So it creates a log of things that go wrong, and then you can use that to kind of.
Is that real time?
Sorry?
Is that real time, or is it?
Yeah, this is real time. Yeah. This is how fast it's running on my computer with the parameters that I showed you. Like this is the gray stuff is a thinking trace. The blue stuff is tool calls. The purple stuff is tool calls coming back. And the white stuff is actually the response in the end. And because it's agents, so it's like it's creating a new context with a new system prompt. That's why you see two whites. So the first white is actually the sub-agent doing the thing, and then when it returns back to the starting point, then you get it kind of twice like that. But it was like the thing about these things is that you can build these things in just a couple of hours. It's not really that complicated, and it's just you can just try things out and see what happens, see how far it goes.
You have sub-agents, but they're sequential.
Yes, exactly. It would of course be interesting to do more concurrency and stuff like that. That would be more relevant, of course.
This is a Llama CPP interface, or
Yeah.
built your
So this is my command line interface. It is using the OpenAI REST protocol that most inference engines support the same REST API that OpenAI has. It's mostly the same, and so.
chat completion.
Yeah, exactly, the chat completion endpoint. And so the only thing I do, as the chunks come back at me, I just do this thing where I just chunk it up and use some bit of coloring to just make it seem like it's alive. But yeah, it's real time, and I'm streaming the responses back into the console as much as possible. It makes it kind of more interesting. It's not alive or anything like that, but it feels like it's doing things. So now the rest of this is just me, like I'm thinking out loud and just thinking about like what can we do from here, like because in the end the context is going to fill up, and so there's this idea about progressive disclosure, which means that you just give it a little bit of, like if the answer is this big, you just give it a little bit of the answer, and then you give it a way to expand it if it needs to. And this is sort of the same way that like, the skills are exposed and the tools are exposed. So like the system prompt contains some general instructions, and then there's a list of tools and skills. And every tool and every skill is just like, okay, it's just a sentence like, use me for this, use this for this, and use this for that. And that's the idea of progressive disclosure, that if I need more information about something, I can go here and I can do that. And that helps it just, fill up the context on demand, instead of just putting everything in the context all the time, right? And then I had I started this with the idea of like, what if I give the thing a way to actually navigate the code structurally and semantically? So like I put all of this is actually in C#. I regret that decision, but anyway, it's what we use at work a lot. So it's like I started just using that. But they ship you can run the compiler inside of everything, and then I wanted like, okay, so what if I give it the ability to like ask the compiler for information about code elements and stuff like that? I thought like, well, maybe that would actually be a helpful tool to have, and it's better to code research. And so that was one thing I wanted to explore. But I kind of realized that there's a better solution to this problem, and that is to not use C#. And the reason for that is actually namespaces and anything which is implicit. So like if you're trying to actually have these things code for you, and you're using a programming language which has powerful abstractions capabilities, I think it's the wrong way to go, because you can create interesting things which are very novel and probably useful, but you have to have the intuition and understanding of what those things do. And they are purpose-built in every code base, and they're kind of invented by creative people doing coding things, and they behave a little bit differently. And the idea that the LLMs are going to understand this and do something reasonable with it, I think is just the wrong idea. Instead, we have Go, which is like simple and very standardized and very, again, homogeneous, right? It's very much the same all the time. It's like, they, like from the start, like we're formatting the code all the way, and like there are very few bells and whistles, it's just code. And the context is very explicit in that if we do fetch something from a package, we have these qualified identifiers that make it very explicit what this thing came from. And usually, if we apply the idea of progressive disclosure and we allow the LLMs to more surgically manipulate code snippets and stuff like that, we can kind of have it work like that. So I think this is the better way to go. Pun intended. Okay, and so at the end of the thing is like, I think you have to take eval seriously if you're going to do this. So like there are all these benchmarks out there that you can play around with. Sure, you can test your stuff on benchmarks, but benchmarks are gamed. And so people will just, to stand out, they will create something which looks good in the benchmark. So a good idea is to kind of have your own benchmark or your own set of like evaluations that you actually run on what you're doing. Because when we do this stuff, it's no longer about, I'm used to programming in a way which is kind of deterministic, and you go from like failing to passing and all that. But this is more a gradient. It's like, yeah, it's 97% okay. It's like, okay, that's better than 96% that we had yesterday. And no one is hitting 90%. Like people are hitting like 80%. And so it's like, okay, that's the Pareto principle. Like 80% there, that's good enough. It's like, okay. And so, yeah, it feels a lot more like research than engineering. And if you really like research and really like this stuff, go for it. But if you're trying to get stuff done, it's just so frustrating. It's so frustrating. Okay, so I was using a gaming GPU from NVIDIA, which is 3 years old. And it worked this far. And so there's this other company that I think is worth mentioning that maybe you've heard of. It's called TensorRT. It's started by a guy called Jim Keller, which is a very prominent CPU architect. He's been around, he's done some really amazing stuff, and he has some really good ideas. And so what they've built is like they've kind of reimagined a hardware stack from the ground up based on, like, they call it the metal layer, and it's all about moving data, because that's what they're doing. Like, we're just moving data around between these things. And then they take all these popular frameworks and they just have compilers that translate onto their stuff. And so you can actually bring in other models onto their stuff and run on their stuff.
That's of course what the big players are doing, even with NVIDIA GPUs. They write to their own intermediate layer to program those.
Yeah. But this is kind of interesting because they're like at some point I guess they're gonna be like, okay, so they had this TT deploy thing they did, and like they were up on stage like, we're gonna crush everybody, like that was their thing. And they kind of did some impressive things, but they're a smaller player and they're not trying necessarily to compete with the edge or the bleeding edge, but I think they will get there eventually. The reason I bring them up though is because this is what they sell. This is their black hole P150A thing. It has what they call 10.6 cores, which is a novel like SoC with RISC-V CPUs and all other kinds of interesting hardware on it. And that's what runs your stuff. You don't program them directly, you program them through their SDK, which is open source, by the way. Their whole software ecosystem is open source. It starts at $139.9. They have a cheaper version of this, but it doesn't have these holes at the end here. I'm not talking about the air intake stuff. Instead, like these things. Because the cool thing about this thing is that I think this runs at 150 watts, right? And this thing has 32 gigs of GDDR6, so that's not HBM memory, so it's cheaper for that reason. But you buy these cables and you connect them, and you can buy 4 of those if you have a motherboard which can support it. And so you can start out like paying a let's say more reasonable amount of money, and then you can just buy more of these and start, scaling out as you want to move to bigger things. Because the thing that TensorTorrent does with their software stack is that they allow you to treat this as a singular, like it doesn't matter if you had 88 of these plugged into a server rack. You could treat them as it was just one GPU, and you can just say, compute this. And they've solved the problem of distributing your data and moving it around between all the cards, which is kind of neat. And their big thing is like they're going to be infinitely scalable by doing this. And I mean, that's a bit of a buzz to say that, but it's kind of what they did. So this is from their TT Deploy presentation, where they're kind of showing off that we can do faster than real-time video. So this is them running an optimized version of 1.2.2. Together there was some collab with a company called Prodia, and they got it to do 33.8 FPS, which is then faster than 24 FPS. So they can kind of manipulate the video in kind of real time, and you're sort of seeing the result here. The reason it looks so crappy is because that's the way they streamed it, and this is a GIF. I think it's 720p, so it's not really high resolution, but still, it's like, okay, so to do that, I think they had like 88 of these black holes wired together. But it kind of shows that if you approach these things the right way, you can kind of scale out when you need, and you can do that incrementally, so you don't have to burn a lot of cash to just get going. Because in the beginning, maybe you can accept that things are moving a bit slower. Okay, fair warning, we are in the beginning of something new and exciting, and I do think this is exciting. Like, I'm a software engineer, I've been around for a long time doing software. I love programming. I don't get to do that as much anymore. I'm kind of sad about that. I get kind of depressed sometimes. I'm like, what I'm supposed to do now? I kind of need to reinvent myself. But we don't really know what the limitations of these things are here. Like, are they really, I mean, is this going to take off? Because it's like, it seems like a lot of people are building AI infrastructure, but I'm not seeing like all the amazing products. Like, we were promised, things I haven't really seen delivered on. That said, there are some really cool applications for AI. I think self-driving cars is amazing. I think that's going to actually end up being a cool thing. And I mean, we have these, like, obviously these models are capable of translating between representations and in ways that we have not been able to do before, and they can deal with messy stuff which we haven't been able to do anymore. Like the language comprehension thing that they seem to be able to do. Like, they're wonderful to interact with. Like, they understand what I'm trying to do so much better than anything we had in the past. So there's something there, but temper your expectations. That's all. That's like, I don't know where we're really going with this. And that's all I had to say.